I've known Steve and Sylvia for almost 30 years. Having done my PhD in this department, Steve served on my doctoral committee. Little did I know when he grilled me in the qualifying exam that I would be introducing this lecture 30 years later. Steve and Sylvia are, of course, well known to everyone in the department. Some of their contributions are readily visible. For someone whose primary occupation is not hydrology, Sylvia undoubtedly has the best attendance record to the hydrology seminars in our department. And I would say also probably to hydrology conferences. Steve himself has had a remarkable career in our department. He joined us from Stanford in 1970 and retired after 40 years in 2010. But retirement can take many forms. And in Steve's case, he can still be found in Wilcox almost every afternoon, reading widely, providing mentorship to junior colleagues, which basically means all of us, and providing support. And what is not always obvious is the tremendous support that they have provided to the department over the years. This lectureship is but one expression of this, and I'm deeply grateful for Steve and Sylvia's support. All right, so which brings me to today's lecture. I'm equally pleased to introduce this year's, I should say, Burges lecturer, our very own Dawn Lehman. Professor Lehman received her PhD from UC Berkeley in 1998 and joined our department in 1999 with research expertise in seismic engineering of structural systems. Her research results have been implemented in codes, design manuals, and provisional structural engineering recommendations. She has authored over 100 peer-reviewed research articles. Today's lecture will cover her research into the partial collapse of Champlain Tower South. She led the technical investigation of this collapse as a consultant to the Miami Herald. The team was awarded the 2022 Pulitzer Prize for breaking news for this work. Please join me in welcoming Professor Lehman.
Let's get to what you came to hear about, which I assume is this building that collapsed in Florida, Surfside, Florida, in 2021. And everybody wants to know what happened. Okay, so just a little bit of history on how I got involved with this, and I kind of want, I hope, as you listen to me talk about this, try to put yourself in the place of being an engineer who has just witnessed something that you didn't ever think was possible. No one thinks that a building is going to collapse in the middle of the night without any external force. It's not an earthquake, it's not a tsunami, it wasn't a huge storm surge, there was nothing. So what happened? So I was interviewed by a number of news organizations, they're listed up here, and I actually also tried very hard, and I hope we can do this together, to not make assumptions just based on one thing. And I saw that a lot of people were proclaiming things that I didn't think they had enough information to proclaim. And so one of the things that I saw was that the Miami Herald had put up this collapse sequence, which I thought was incorrect. And so I wrote to the lead author of the paper and said, I think you might consider pulling that down. I thought, she probably wouldn't respond to me, or she'd just say, yes, thank you, and go on her way. But in fact, instead, this woman, whose name is Sarah Blasky, she actually came and said to me, well, what do you think happened? And I said, I don't know, but I know that there isn't enough information yet to know. And so over time, we built a collaboration, which is probably one of the best collaborations I've had in my personal career. I'll talk about that a little bit. But what I really realized, and the reason that I wanted to work with the Herald rather than another institutional journalist paper, is because this is sort of what people saw. So this is the building on the left, okay? So this building has an L shape to the tower. So when I talk about the tower, I'll talk about this. And you can see there's a pool deck here. This pool deck is just one story. And underneath this entire site, there's essentially a garage. So this is what it looked like before. This is what it looked like after. And that's about all any of us had to be able to say what happened. So can you tell me what happened just by looking at that photo on the right? I can tell you a few things that are important to me. One is this is a big pile of rubble. Second is this doesn't look damaged. And third is that I can sort of see structural components in there. So those things are going to be important to us. And this is what is getting hit. The newspaper is trying to publish all of these articles one after another, and people are scared because there are a lot of buildings, especially in the Miami-Dade area, that look like this. This is not an uncommon system where you have a tower and that is this specific structural system, which we'll talk about. It's called a slab column system, and it has a pool deck. So if this is what your newspaper looks like, you're scared. I mean, and I can't blame them. So what approach should we use? If I'm telling you that that photograph isn't enough, what else do we need to understand what happened? So I think we need a couple of things. So first, we need these damaged photographs. And I spent a lot of time looking at different photographs to the point that every morning I was looking at photographs and my kids would come downstairs, you know, because it was COVID, right? So they were all home. And they would say, "Are you looking at that building again?" And I would say, "Yes." But I have found through my work in earthquake engineering, you have to look again and again and again and again, because you can make assumptions based on what you see, but you only get to see one moment in time. And that is at the end when the building is damaged or has partially collapsed or fully collapsed. So we want those photographs. We also need drawings. Those of us who are engineers, we know that one of our main communication tools are structural drawings, and we'll look at those. One thing that I didn't realize that we needed, but Sarah Blasky, my colleague at the Miami Herald, knew that we needed, was to establish a timeline. And that timeline actually became really important, and that's one of the first things I'll talk about. And then, you know, since I am a structural engineer, I wanted to try to understand what happened. Photographs alone aren't enough. Drawings with photographs is not enough. We really had to develop a model to try to explore what happened there. And I was fortunate. I had a PhD student who was working with me at the time, Nikki Lewis, phenomenal engineer, phenomenal modeler, and she and I spent probably about 4 weeks or so modeling something that they should have given us a year to model. The other thing that I want to talk about with a model, and this is an engineering model, this is not something that just shows the geometry of a building, for example, like an architectural model. This model actually has properties of the materials themselves. So obviously, if I know what the answer is, and we all know what the answer is, right? There was a partial collapse, the pool deck collapsed, the tower partially collapsed. So how do I validate it? You know, I saw a lot of people in the first month coming up with quote unquote models that simulated this building. They didn't simulate the building, they just ended up with the same damage scenario at the end. But we're interested to know what happened. And so we want to look at that. So this is the timeline. All right, so this is our first introduction to being a structural engineer, okay? So lesson 1 is going to be about drawings, and this, so you can see over here the tower has an L shaped to it. This is a plan of the tower. So this is the very east side, this is the very west side, and you can see there are numbers. Each of these are a unit. And you can think if you're on level 1, this unit here would be numbered 110. The unit to the right would be numbered 111. I'm pointing those out because those are actually important units. Oh, okay. So this is an elevation. Okay, now I'm standing to the south of the building and I'm looking at the building as it goes up. And this is the southern portion. This red line actually shows where the actually extent of the collapse is. We'll look at that. That is actually where there's a wall. And this bottom level, which I was talking about before, unit 110 is a gym, and unit 111 is where the Near family lived. And we unfortunately have to put some names to this tragedy that killed close to 100 people. But it's important because these are the people who are going to tell us about this timeline. Cassie Stratton, she lived on the 4th floor in this same stack where the gym is. And there was a woman who lived on the 6th floor in this same stack where the Near family was. Okay, so around, I know, 1 a.m. in the morning, but around 1 a.m. in the morning, the Near family had just gotten home. They were a particular sect of Orthodox Judaism. They were out because they were celebrating the high holidays. And so they had come home, they were hearing some strange knocking noises. Sarah Neer, the mom, lived with 2 of her children. Gabe Neer is one of them. And the security guard also heard these strange knocking noises. So at 1:14 a.m., so they were hearing this between 1 and 1:14 a.m. At 1:14 a.m., there was a couple that shared their time both in Argentina and in Miami. They're actually telenovela stars. And because my colleague, Sarah Blasky, understands Spanish, she knew what they were saying. They did not want to be interviewed, so I want to respect that. But what's important is they drove in to the garage at 1:14 a.m. They didn't see or hear anything, and they took the service elevator up. And when they took the service elevator up at 1:15 a.m., they got lucky because the service elevator always stops at the first floor. And so as soon as that elevator reached the first floor, they heard this thunderous clap like others did, and that was essentially when the pool deck here collapsed. So you can see this is the tower, and this is where, of course, all the people live, and this is the pool deck, and these red dashed lines indicate the extent of what we can see, which is really important as we try to understand what happened. We don't exactly know what happened as we move towards the tower because that is where that rubble pile is. So you can see that at this point that this pool deck fails, Gabe Neer and Chani Neer, who are in Unit 111, they actually move and run out. The security guard hears a loud boom. And then Sarah Neer, who was talking to the security guard to try to figure out what those knocking noises were, runs south, and she comes to a place on the first floor where you can see out, and she saw this pool deck collapse. And so you can see everybody who is on this first floor who have heard this, they exit the building. And then, to confuse all of us, there was a video. I think this video was on TikTok, but I can't be sure. But let me tell you, social media has become incredibly important for these journalists. There was a woman who was just to the north at a hotel who had taken out her iPhone and took a video into the garage. And you can see that there is what looks like water, and there's rubble, concrete rubble on the ground. I would say that until we understood this collapse sequence, we thought that maybe that actually had failed before the pool deck failed. And at 1:16 a.m., as they leave, sorry about that, and this is essentially looking into the building. This is from the Herald. You can see that rubble that we had seen before. There had been, over the years, a lot of reports of a lot of water intrusion, which is going to be important when we start thinking about how that impacted the failure modes. At 1:20 a.m., Cassie Stratton, who was on the 4th floor in that 10 tower right above the gym, which is going to become important, called her husband to say, "Oh, I'm so glad that we didn't leave our cars in the shop because the pool deck, caved in. There's a sinkhole." I think that's a fair way for a layperson to describe it. And what she told Mike Stratton was that as the pool deck failed, it was coming towards her, which is also important. The other thing that when Sarah and I talked to Mike Stratton, we learned is that there was a building that was just to the south of this building and an easement between the two buildings, and that sprinkler or irrigation system kept watering this portion of the pool deck. So it was just to the south of the pool deck, but it was watering the pool deck. And again, this whole concept of water intrusion through this pool deck is going to become important, especially when we try to understand what might have happened. And then at 1:22, so 2 minutes later, the tower collapsed. And it collapsed through this portion of the building eventually, and the whole eastern tower collapsed. The western tower remained intact. There's a structural wall here I'm sure most of you know what a structural wall is, but you know, if you think about having something that's very wide and high and thick, that wall can actually provide quite a bit of stiffness, especially if you think about wind loading, which is important in this region. So that wall remained intact, but the rest of the building failed. There's another wall that we'll look at in a minute. So you can see that when the security guard helped Ms. Montego leave, you can see that they couldn't actually get out the front, and they had to kind of weave their way out. And that also becomes important as we look at damage in the building. I've put this up here because this is not an engineering aspect, but it is an unfortunate truth of this tragedy, which is that because the security guard was not trained in using the alarm, and we know there's 7 minutes between when the pool deck collapsed and when the tower collapsed, most likely people's lives could have been saved. And if you heard at all about the lawsuit, you know, a part of the settlement was with the alarm company. I just want to point that out. If you're interested in learning more about any of this, the Herald really has done a great job on that. Okay, so we have a timeline. We know that there were 7 minutes between the pool deck collapse and when the tower collapsed. And we know when the pool deck collapsed, it was moving towards the tower, not away from the tower. So I still haven't told you what happened. You still don't probably have an idea what happened. We're still sort of here, right? Except that we know that this pool deck collapsed first, and it collapsed towards, or progressively collapsed towards the tower. So in order for all of us to think about these things, I want to use some information that I know and anybody else in this room who's a structural engineer and understands reinforced concrete knows. So this happens a lot after earthquakes, and a lot of you might know I have done most of my research in earthquake engineering. It might have seemed strange that I decided to take this on. But one of the things is, you know, I studied this building actually with a colleague of mine who's here, Laura Lowe's, and we tried to understand what happened to this building. But if somebody just shows you these two photos, you know, what do you see? You see this building standing, and then I see this building that's collapsed. Looks like something's still intact. Maybe that's the stairwell. A lot of times we put walls around the stairwell. I can see that there are columns with some kind of damage, and then an undamaged length. But other than that, I can't say much about it, especially in this collapsed state. But if I take a building like this after an earthquake, so this was after the 2016 Southern Taiwan earthquake, this is the building after the earthquake, and I can go in and look and see, oh look, there's the column. The column looks like it has some diagonal cracks and some vertical cracks. Remember, the column wants to take compression. This column has a similar sort of damage pattern. This is inside the building. You can see that there's damage here. So at least when I have this level of damage, I can actually say something about it. Now, how can I say something about it? Well, I can say something about it because I understand how reinforced concrete behaves. And in the next 6 slides, you're going to understand too. So the first thing we know about concrete is that it's good in compression. This is a cylinder. We like to test concrete cylinders to figure out the strength and the stiffness. One interesting thing here is, in addition to these vertical cracks, you can see there's this diagonal pattern, and that will become important. The other thing to know is when concrete fails under a compressive load, it can actually be quite explosive. So we don't really want that to happen. So what should we do? Well, a lot of times we like to use structural members so that they carry load, right? For example, you know, this roof, somebody needs to be able to design this for the load we expect, especially the dead load, which is the self-weight, anything that we know is going to be in the structure permanently, and live load. Those are unexpected weights, right? Furniture, people, equipment, etc. So we tend to have something that spans between maybe 2 columns. It has a load on it, and the top here is in compression, and the bottom's in tension. It's not always that way. But as we said before, since concrete's not good in tension, it'll just break through. So what we do is we consider how these forces are being carried, and we actually place steel where the tension demands are. So you can see here, this is a beam that's being subjected to that same point load. The compression forces are at the top. You can see that there's some damage here. But in the tension forces, you can see there are these cracks that are vertical, and we place the reinforcement here to take those forces and also to keep those cracks closed. And that's also important when we think about corrosion. If we had a lot of reinforcement that was so much, huge area, really strong, then we might end up actually changing our failure mode to compression, and we don't want that. So in general, anything that's bending, a beam, a slab like this, we will see cracking, and we'll place our reinforcement to sustain the tension. The other aspect of concrete that really is not welcome is shear. So I talked a little bit about this diagonal strut, because one of the ways concrete carries compression is through strutting action. So you can see here, this is a beam that failed after an earthquake, and you can see these diagonal cracks that are very open. But you can't carry compression perpendicular to the crack because the crack's open. So you need to carry compression along the crack. And so that's how we carry shear in concrete typically, which is also going to become important. The last thing I want to talk about is bond. What is bond? Well, if I have concrete and I put steel in it, I need to transfer those forces between the steel bar and the concrete. And so if you've ever seen a reinforcing bar, you might see that they have what we call these deformations. And so those deformations are there to transfer the force from the steel into the concrete and vice versa. So it's almost like another material. The concrete has a strength, the steel has a strength, and the bond also has a strength. And if you have high bond demands, you will run into trouble. So you need to have bars that are long enough that allow that transfer to happen. And maybe if you start running a lot of water through this slab or this beam, the concrete properties might not be what you assumed in your original design. Now, I don't know that, but that is possible. The other place we need bond is when we want to fully anchor this bar, right? So maybe you've seen after an earthquake, we will have vertical bars from a column going into a foundation, and if those bars aren't long enough, they will just pull out and allow that to move over. So these connections are going to become important. So compression, concrete's good in compression, stiff in compression. Tension, anytime we have tension, we really want to have an orthogonal bar to the crack to take those stresses, keep those cracks closed. Also talking here about bond and making sure that the bar is long enough to fully transfer the force from the bar to the concrete, and also shear, which concrete likes to carry at an angle, okay? There, everything you need to know about forensic engineering of concrete, right there. Okay, so now what do we need to do? Well, before I start looking at all these pictures, let's take a little gander at the structural drawings. So again, this is this L, right, that we've been talking about, this tower. And the red square rectangle is around the portion of the tower that collapsed, and the green shows the portion of the tower that's still intact. What kind of system is this that's holding this building up? Well, it's called a slab column system. So it's essentially a flat slab. So I'm showing that above, and a column, showing it also below in a drawing and a sketch. In addition, sometimes we will use beams. These beams help to strengthen, but they also help to stiffen. Have you ever been in a building, or especially sometimes at the airport, and you can feel the floor vibrating? Turns out people don't like that. It's not going to fall down, but it turns out people just don't like that. They don't like to feel this floor vibrating. So a lot of times when we design something like a slab, we actually design the thickness to make sure that we don't have those kind of vibrations. So not everything is designed for strength. But typically, when we design a slab column system, we want the slab thickness to be a function of the bay width. That is, with a width between these two columns, because if that gets longer and the slab is still thin, it's going to deflect and it's going to crack. Those cracks are going to open. Doesn't necessarily mean the building's going to fail, but it's not going to be serviceable in the long term. So sometimes beams can help you. The other thing is that we know that slab column connections can be weak, and so sometimes we'll put additional reinforcement and concrete around that in the form of what we call a capital. That didn't happen in this building. Okay, so it is a slab column system, and there are some beams, but not that many. This is a drawing. I'm sorry if this is the first time you've ever seen a structural drawing, but this is a plan of the building. It shows this exterior wall. This exterior wall is a perimeter wall. It's a retaining wall. It keeps the soil out. Sorry for the geotechnical engineers. We just don't like soil in our building. But so we have this retaining wall. That's going to become important. You can see I have shown this southern retaining wall in blue. That is one of the most important components for us to look at. This is the core wall that I was talking about before. You can see it's in the north-south and the east-west direction. There's also a stairwell wall that's in the north-south direction. These columns are larger. This is in the portion of the building that remains standing. They're 2 feet by 2 feet. These columns that are just supporting the pool deck are smaller. And that is what we would expect, right? Because these columns are carrying a full building on top of it, and the pool deck is just carrying the demands of the pool deck. And remember, there's a garage underneath there. So those are just one-story columns. Now, there are some larger spans, anywhere kind of 23 to 28 feet. I will say that these clearly are not the drawings that were used to build the building. How do I know that? Because this is not what the pool looks like over here, and there's no jacuzzi. This, the way we like to talk about plans a lot of times as structural engineers and architects and contractors is we refer to column lines. These columns are very important. They're typically set by the architect. So there are column lines in the east-west direction that are A through Q, and there are column lines in the north-south direction that are 1 through 14. And this column line here, 9.1, is very important. We know that's very important because it's framing the perimeter of the tower to the south. So this is the delineation between this pool deck region that we know failed first and the tower itself. So those are the important aspects of this. And I will refer to that column line, 9.1. I might call it the perimeter beam because there is a beam there. Like I said, these slab column systems, they do use beams. This is the level that we're going to end up focusing on. This is level 1. Why am I focusing on level 1? Because that's where the damage initiated, and also that's where I can see structural components, unlike the rubble pile where I really can't see much at all. So again, the column lines are the same, and this is the portion here that is our region of interest where the pool deck failed. This is a 9.5-inch slab, and I will tell you that a 9.5-inch slab is not thick enough for these spans. So just out of the gate, we know that this building is under-designed without checking anything, doing any fancy analysis or anything. We already know that, and I'm sure every engineer who went through knew that too. But it is not easy to thicken a slab in an existing building. So. The other aspects that are going to become important for us are the connections. So remember when I was talking about bond, we want to anchor these connections. One thing that is interesting and important to note is this slab is actually connected to this exterior wall intentionally. Whether or not they actually use it in their analysis, I don't know. This building was built to a 1977 code. Clearly things have changed since then. You can see here that there's a big square around the column. It looks like that might be that capital that thickening that I had talked about before, but that's actually not what that is. That is telling the contractor that this reinforcement that's denoted within that square, 25% of it should go through the column each way. And that is really important to be able to connect that slab to that column, right? So these connections are important for us. And this is just a detail of the connection. You can see here, this is the slab connecting to either an exterior wall or a column, and you can see that they've hooked that bar, right? They hooked that bar so that we have that anchorage. So if something happens, the slab will still stay attached to the column. Okay, now we're going to get into the interesting stuff. Now that we're all educated, all at the same level, we all know how to do this. So the first thing we want to do, now that we understand the drawings, is look at the building. There were so many people during the height of COVID who were called in to do a rescue effort. is really amazing. The same thing is happening in Turkey right now. So structural engineers are actually they're very integral to being able to take apart a debris pile so that the people who are doing it remain safe. And I'm just very grateful to those people for doing that. It was really a hard job. So here we are with this building again. This is an arrow just to say that that's north. And you can see here, this is actually after the building collapsed, of course. I'm not exactly sure when. There are a couple of things that you can see, but notice these cars are still where they were before the building collapsed. This is actually a structural wall. And you can sort of see in here, these are some columns. So I can see structural components, but I can't really say too much about the damage pattern. And this just links what we're looking at to the drawing. So this is that perimeter, that core wall that I was referring to, which is here running north-south. You can see this is that stairwell wall. No, a wall should not ever be able to disconnect like that. So again, connection's clearly an issue, and this is these exterior balconies. They were corroded, but that's not what happened and contributed to the building. This is if you were actually standing north and looking south. There's a building here, 87 Park. That building is actually in a different city called Miami Beach. And if you want to read more about that and how it might have come into what ended up happening to this building, there's a lot in the Herald on that. This is the structural wall that I referred to before. And the interesting thing for me is I can see that the slab, there's just a very clean surface, almost vertical, of the slab that is been connected to this wall. You can see here those top bars. That means there's a tension force at the top. They fractured, but in some cases those bars actually remained intact and the slab just pulled off of them. And it looks like it could be a bond condition issue. So then I want to go down and look at what happened to the pool deck. I'm interested in this region here. You can see there are planters that actually are not the same configuration as these planters, but clearly the landscaper got to get the right pool. I don't even know what to say about these drawings. This is not an example. I know you're all newly fresh structural engineers, but this is not an example of how to make drawings. These are horrible drawings. Okay, so here's where we really want to start trying to understand what possibly could have happened. So just notice here, and this pool, I don't know if you read about the pool. People said, oh, the pool's corroded. Was the pool corroded? Yes. But the pool's still intact. And this whole portion of the pool deck is still intact. And this portion of the pool deck collapsed, even though the connections here and the connections here are the same connections. So it can't just be the connections. Something else must have happened. If I look at it from my point of view, having gone through these photos a lot, I see that the slab has detached from the southern perimeter wall, so that continuous connection has failed. There's a strut. Remember how we said concrete likes to carry forces through some struts, so it's strutting to a wall in the jacuzzi. The jacuzzi does have a thick wall. That angle continues until it actually, the extent of the damage region runs north-south, and I think there's a construction joint there. What's a construction joint? I forgot to tell you that. Okay, this is the bonus in the class. So a construction joint is when you cast part of a slab, right? You're not going to be able to cast the whole thing at once, and you want to cast the next part, and so there's a joint between those two castings, and usually we put reinforcement through there. So we will look at that. You can also see all of these white ellipses. Those are columns that are sticking up through the slab. Remember, there's a garage underneath here, so that slab has fallen. It probably hasn't fallen all the way down to reach the floor of the garage because this is Miami, right? These people like their cars, especially their white cars. So there are, one of the reasons they make this site big is that they want to have a parking space for every unit. So, and then over here, I can see that there's this brown paint or whatever, I don't know. This color is all over Florida. I don't know what to call it, but they seem to like to paint everything this brownish, pinkish color. So that's actually above the level 1, and this white part is below because that was, again, part of the garage. This is what it would have looked like if you were there that night, and you can see that over here, this is the portion of the building that remains standing, but we've lost the connection of the column and the slab. You can also see this facade here, this treatment on top of what is actually a surface level parking. It's actually valet parking. Is still intact. So the extent of the damage to the west does go into the portion of the building that remains standing. This is the same during the day, and this is important. We'll look at that in a minute, but see that angle? So these bars were originally in the slab. They're still intact in terms of the column, but the slab has sort of fallen off, and you can see that there's an angled damage pattern where the slab was. In terms of column damage, people like to start with columns. Columns, they take axial load. If one of them's missing, the whole building's going to go down. We'll show that that's not true. But you can see that it looks like they poked through. So I don't see any kind of slab that's still attached to this column. This is just a one-story column. You can see here they hooked the bars. Again, those bars are hooked for anchorage to keep that slab attached to the column. So we see a lot of that sort of damage where the slab has pulled off of the column. Now I'm going to try to incorporate a little bit of testing to show what happened. So somebody took a slab in their lab and they built themselves this basically salt bath, and they corroded these bars. And when they corroded the bars, you can see what it looks like. There's essentially a failure plane, a horizontal failure plane, because those bars were corroded. Same thing here, might be hard to see. This is the eastern extent of the damaged region, and the bars have all pulled out, these bottom bars. This is the construction joint that I was talking about before. This is one cast, this is the second cast, and that's the reinforcement. And you could see in some places some reinforcement going through there. You can also see reinforcement at the top of the slab. So it does seem that there's the potential, and this is the other side. So there's the western extent, and again, you can see that same sort of damage mode where these bottom bars have pulled out. So one of the things that we do in reinforced concrete is we put a concrete cover beyond the bar to prevent corrosion. Unfortunately, when this building was built, the cover that was required within this garage was only 3/4 of an inch. It was not enough to keep these bars intact and prevent them from corroding. And then the last thing I want to talk about here is this connection. This is pretty well understood damage mode where the slab has detached from the column. This is just an example from an experiment, and you can see when they cut it apart, there was this diagonal crack that we had talked about before, right? Compression, concrete likes to carry compression through that crack, and then this horizontal crack, which is sort of like this plane of weakness. And so you can see there aren't any bottom bars here, so there's really nothing to keep that slab connected except for potentially the bars, but you can see here that, again, there are bars that are attached to the column and they slipped off. This is a close-up of the pool deck. I just showed this because a lot of times people were focusing on the corrosion within the pool deck. Within the pool was just very thick wall. Yes, it was corroded, but you can see that it wasn't damaged. So the last thing that was really important to me and that I spent so long looking at was this southern perimeter wall and the damage along the wall. Because I know that if you have a connection and that connection has the same properties, then the damage should look the same all the way along the length of the wall, but it doesn't look the same at all. Here you can see part of the wall is missing. It looks like there are chunks of concrete. When I go over here, it looks like there's gravel. There is gravel because there's gravel in the easement that's just to the south. So these are the things that we ended up focusing on. This is an image from the Miami Herald looking at these columns that have poked through and also trying to understand what happened in that wall region. So this is an image from the Herald where you can see that here there's just a vertical shear plane, and as we move west, we see a different type of damage. Here it looks like somebody came in and added reinforcing bars, which is what I think they did. And as we move along, you can see that the gravel that's in the easement is exposed. On the right is a slab wall connection test that I just showed to show that the kind of damage that we would expect here is just this vertical plane of damage between the wall and the slab. So we can see that that's what we would expect, but not the kind of damage that we saw before. The last thing, somebody, I don't know how, flew their drone on this site after it was cleared. I'm thankful for it because this really was what gave me a better understanding of this wall. And so here is the area, like I had said before, that looks like somebody came in and cut in and replaced some of the reinforcement. You can see these areas where it looks like, you know, the slab reinforcement had fractured and then just distressed the paint on the wall. You can also see here there's a different damage pattern where these reinforcing bars had pulled away. So one of the things that came out after Nikki and I had done our modeling is that through the discovery, they found that the contractor apparently didn't care about that wall. So it does lead to the idea that perhaps somebody damaged this wall, maybe during construction of the 87th Park building, and that might have been why we saw the full failure that we did, because that connection wasn't intact. And this is just a description of what I have been talking about to date. Okay, so I want to end. Now this is like PhD. Now we're moving on to PhD level work. So I want to end with, how do we understand what happened now that we've seen all of that? So I came in to this not to model the full building, not to model the full collapse. That's what NIST is doing. What I wanted to answer was, how does damage in the pool deck 60 to 80 feet away from a building result in damage in the building? Right? It seems like I damaged the pool deck, it shouldn't be impacting the building. And so that's really what Nikki and I focused on. This is just to say we used a peer-reviewed model, and you can see here, this is a column, and there are these little squares or concrete, and these bars are embedded in those concrete cubes and their reinforcement. And we essentially Nikki really, built a full model of level 1 with a very refined area where we know that, basically this is one of the eastern portions, right, of the damaged region. This is a western portion of the damaged region. And we don't really know what's happening in the building, so we actually did a bay of that building with a very fine mesh as well. And then this surrounding it is just a more simple model. These models are very computationally intensive. We used a high-performance computing cluster, and some of them took 20 hours to run. So this is also an evaluation. So we only put load on this level 1, as well as the additional load from the columns above, but we only put on the loads that were there. And we only used the properties that were as designed, except for one thing. So essentially, I'm going to look at 3 different models: the reference model, the model with taking some of that steel out and replacing it like we saw in that wall, and then corroding the reinforcement. And I will try to present a couple of very simple images. So this is an image of the vertical deflected shape, right? So we're pushing down. This is the plan. This is the jacuzzi. This is the core wall. And that's the edge of the building. And each of these colors, as they get darker, is a higher state of deflection. Remember the bars that we've been talking about a lot, that we need to connect one component to another, to take the tension forth, to keep those cracks closed. We also want to look at what the stresses are in that. And then we also have the crack pattern at the top of the slab, and this is at the bottom of the slab. You can see these columns here, and this is as if you were in the garage looking up. So this is what the Herald did with what Nick and I were like, oh, they're fine. The Herald had to color them pretty. But essentially, this is what we saw just at the as-built. And if this is actually as-built, it's hard to say. But you can see we have a lot of cracking around the columns. This is exactly what we would expect. Concrete is going to crack under load. So, you know, the fact that there are cracks is not the issue. The issue can become when the cracks are too large or the system has degraded. The other thing we would like to look at is sort of what's going on with the steel. So the steel yields at about 60 KSI, and you can see that there are bars just under dead load alone without any load factors that are reaching yield. So this is already a very under-designed building. It stood for 40 years, but it's an under-designed building. So sometimes people just said, well, we think maybe someone came in and I don't know, they took out a column. I'm not exactly sure. This is from the New York Times, and they were claiming that this column, which is at column line M and 11.1, the intersection was missing. You can see where that is. It's pretty close to the perimeter of the building. What happens if you take a column out? Well, if you take a column out, it turns out that you get a lot of deflection where you took the column out, but you don't really get anything else. Remember that the pool deck started to fail somewhere here and move towards the building. So just taking the column out alone is not going to do that. So the next thing that we did after trying a lot of different parameters is, well, what would happen if somebody actually took out reinforcement? This was before we had any idea about the contractor admitting that they damaged the wall. So Nikki and I took this column line that we had been looking at and took out reinforcement on either side, and we added additional reinforcement because we saw that in the image of the site after it had been cleared. And this compares what the as-designed condition is to what happens if the steel is removed. You can see that there's a more uniform deflection of the slab along the length of the wall. We did also get some increased deflection in this bay relative to here, which makes sense, right? This is a continuous system. So what happens in this bay can impact that bay. That is one of the reasons that we modeled the full first story. This is a comparison of the tension damage. This is what we were looking at before. And over to the right, you can see that removing that steel put damage into the building, and it did it at the gym. And so you can see here that, you know, it's not a very significant crack, but it does suggest that there was unwanted cracking before the building collapsed. This is if you were down below looking up, you can see that there is some difference in the crack pattern. But again, remember what we're trying to do is say what happens, how does damage in the pool deck result in failure of and collapse of a building? How does that damage impact what's happening in the tower? So this is the reference reinforcement. You can see if we remove some of the steel here, the connecting steel between the slab and the wall, those bars that are connecting the remainder of the wall to the slab actually are more highly stressed. So we came up with a hypothesis from this. The idea we had was that the damage started at the exterior, at this continuous slab wall connection, and then it moved north through these slab column connections. So once this continuous connection was damaged, we would increase the demand on these slab column connections, not just force, but also deformation, which could result in failure of those and then resulting in damage up into the building. Now, a number of folks have been concentrating on the area that was in front of the near unit, and I started there too. But there are a lot of beams that are framing orthogonal to the perimeter beam in the tower here. And reinforced concrete is smart. It really is. It can change its angle as it's being deformed, and there's no reason that it would want to have to go through all that structure when it could just go through that flat plate and enter into the gym. So, why do I think that is also reasonable? Well, the other thing is that, this is the Herald's anatomy of a collapse. But this is a structural anatomy of a collapse. This is a really nice set of tests that were done. And what this testing did was it had a slab column system, just like we're looking at, and started the damage, or essentially released the load, but damaged an exterior column versus an interior column. When they damaged the exterior column, they got collapsed. When they damaged the interior column, it was still capable, the slab was still capable of sustaining those forces. So what did we do? We looked at corroding the steel. Steel corrosion, as you might know, can change the area, but we didn't do that because we didn't know how much area could have been taken off of those bars because we didn't have access to the site. But we do know that corrosion can reduce the strain or the deformation. So if you think about pulling a rubber band, for example, at some point, if you pull it enough, it will break. And so what is happening is the corrosion is affecting the material properties of the steel such that you can't pull it as far. It's called ductility, but essentially we've worsened the condition of the steel, and the steel is really important, as we know, to connect the slab to the columns, the slab to the wall. We also made sure that we only included corrosion in the regions where we saw it, so at the slab wall connection and also at the construction joint. And when we do that, you can see just from the vertical deflection, this is the reference, you can see how much deflection we have in the slab. Obviously, this is obviously fractured, so there's extensive deflection of the slab, but there's also more deflection in the building itself. And remember, that's all we're trying to investigate. How does damage in the pool deck result in damage in the building? The other thing that came out of the discovery was that this column line, which has the planters, which is the column line we've been looking at, had damage just a number of days before the building actually collapsed. And this damage was in the form of this crack in the planter. And that could have been because this column here has water damage on it that has discolored the paint, as you can see, and that water is just going through the slab column connection. Could there have already been some degradation to the slab column connection? And that actually contributed to the failure. This is just an image that the Herald put together so that you know where we are. We're looking at that column and this planter. This is that surface level parking that we talked about, where this western portion of the building primarily remains standing. So there is evidence now that there might have been previous damage to this building that would have weakened this portion of it and allowed for this collapse. This is what happens to the crack patterns, and this is what happens to the reinforcement. You can see all of this reinforcement has fractured. That's why it doesn't show up with a lot more stresses, higher stresses at the slab column connection all the way into the building. So you can see the stresses in the slab reinforcement in the building are lower than when we add this corrosion and we get damage and failure of that connection. So, if any of you are really interested in this and understanding more about it, because I clearly didn't answer the question of what happened, I would encourage you to follow NIST. They have, I think the sports analogy is a dream team. So they have folks looking at the building. They've tried to preserve as much of the debris as they could, and they also were going to test that to understand the properties of the concrete and the steel, which we know are important. They have a great group of geotechnical engineers who are looking at the impact of the surrounding site and the soil, as well as a team looking at just the structural engineering of the system. And I want to end with a photograph of my colleague, Sarah Blasky. This is where she called me on the phone to tell me that we the team had won the Pulitzer Prize. It was just such an amazing moment, and she's just been such a fantastic colleague. And we gave a presentation together. I know for a lot of us journalists, you feel like they're not necessarily listening or respecting what you're saying, but if you find the right journalist, especially an investigative journalist, I think that you can actually create a great partnership. I think Sarah and I did that. She's so bright, she caught on so quickly. She was just such a joy to work with, and she pushed me. Because when she told me she wanted me to model this building, I was like, no, people spend a year doing that. We don't have, no, Dawn, I know you can do it, I know you can do it. So the real reason I could do it is because I had Nikki working with me. But it was just a great team. And with that, I would like to thank you all, and again, just so grateful to Steve and Sylvia and the department for inviting me to give this lecture.